to another AQA AS Chemistry video, and today we're going to be doing the second part of elimination reactions. So the first part was to do the elimination regarding halogen alkanes, but this time we're going to be doing the elimination reactions of alcohols. So far we've seen how to oxidize alcohols to get aldehydes, ketones, and carboxylic acids, but we can also get alkenes from alcohols. And I'll just show you the general equation for that here. So you have the general formula for an alcohol, obviously CnH2n plus 1 plus 1 OH plus I would say plus really. You can undergo a reaction to form an alkene. I was about to say plus here, but it's not actually a plus. It's actually a catalyst that you use. So I wouldn't say it's a reactant because it doesn't get used up in the reaction. So a H plus and acid catalyst is used. So before I was talking about the hydration reactions, and that's when you gain water. So hydration is when you use water to break a compound down, and usually to form alcohols. Whereas you can do, I remember saying that reaction was a reversible reaction because you can also do a dehydration reactions where you're using an acid catalyst to form water. We'll use acid catalyst in the reactions for this dehydration reaction where you're forming water, you're removing water. Obviously the acid catalyst doesn't get used up, so the H plus, you'll get an H plus from your original alcohol. So these are just elimination reactions where water is eliminated, as I said before. The equation shown above is how to collect an alkene from an alcohol from a dehydration reaction under acidic conditions. I should say just. There you go. So the mechanism for an ethanol dehydration reaction. So if we have ethanol. Yes. Right, so this ethanol, so you have your acid catalyst, right? So it'll be a sulfuric acid, for example. And your ethanol actually acts as a nucleophile. And it's always remember to go from your lone pair of electrons to your positive charged electrophile. In this case, it would be the H plus. I'll probably draw this H plus a bit closer to. Let me put this H plus a bit closer to here. There you go. This is a reversible reaction, so I'll put this. You form this intermediate. I'm drawing this exactly how you should do it in the exam, so that you don't make. This is the exact way that you need to do it in your exam anyway. Right. This now is going to be positively charged because, and the only other way, because it only wants to form 2 bonds. So now the only other way for it to become, in order for it to have only 2 bonds, is that it could break this bond between the hydrogen and oxygen to like there. However, that's what we just started from. And I guess some of them could do that again. Some of them would do that. However, it's more likely that this reaction would happen where the bond between the carbon-oxygen bond will go to here. The electrons in the carbon-oxygen bond will move towards the oxygen. And when that happens, you've now released, you formed this intermediate. Actually, write that down. My bad. You form this intermediate here, alright? And now you have water here, But in order for this to this needs to form, you know, a double bond, because you can't just have this positively charged carbocation here. So you get one of the bonds from here, this carbon hydrogen bond, so you can actually, and this is how you form your alkene. So you have your water here, carbon carbon double bond now, hydrogen 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 hydrogen, and now this H plus, you've now this, so you have your, obviously your water still here, and now you've now lost H plus, and that's what I mean by the catalyst doesn't get used up in reaction. It's always getting reformed, that will get attracted back to a sulfate or whatever acid intermediate that you'd have. Note the action of the H plus from acid catalyst never gets used up, and note how the positively charged carbocation from the alkane collapses to form an alkene in the final step. The action of the acid catalyst. So the reaction requires an acid catalyst, so the catalyst is protonating the OH minus with the hydroxide ion, which is the alcohol functional group, to make it easier to eliminate this group. And the acid catalyst is reformed when the H plus is lost, as the alkene forms in the last step. So as I just said before, this gets reformed in the last step here, as the alkane collapses, or this carbon hydrogen bond gets attracted to form the carbon carbon double bond here, in order to make this more stable again, because this is a carbocation here, and that's very unstable. And that, when that happens, you lose H plus, and that can be used to regain your acid again. So why do we do this? Because so why we do this? Because we're good at producing alcohols without using crude oils. So it means that we can just, you know, this is another alternative of doing it, meaning we can get alkenes without cracking the alkanes from crude oil, and also meaning that we can polymerize these alkenes and make polymers without using crude oil. So when I ask you about uses of this method, like, remember what you're forming, what you have. Whenever I ask you why you have this something, or why is it better to do this, or what's the usefulness of this type of reaction, is that you have to remember what you have, where you got this, what you're forming, and where you got it from. You know, you usually get alkenes from crude oils. The reason why this is beneficial, because you're getting alkenes not from crude oils, which is a finite resource. You're getting it from alcohols, which is more abundant, let's say. And what alkenes used for? They can be used for polymerization reactions, to form polymers. We don't have to do cracking, which is not environmentally friendly. So yeah, that's it really. That's all I have to say. Hopefully this video was helpful.